Hello and good morning. So today we're going to be looking at sine and cosine functions, and it's hard to understate how important these two functions are. Since they're connected to triangles, and we can draw triangles inside of circles, these are kind of like the building blocks of anything that's geometric, anything that has any shape that we want to study in math. Triangles and circles are going to play a starring role. And so then sine and cosine will also play a co-starring role. In kind of a big picture view, what sine and cosine measure is the proportion or percentage to which you are pointed in the up or the right direction from the origin. But we're going to get into how that connects to the idea of the Ferris wheel, rotation, and all those things. But I just wanted to throw that out there, that these are a lot bigger than the context than we're working in. You'll be playing with these things all the way through Calc 3 and beyond if that's your trajectory. So what we're first going to do is look at how to orient ourselves, some conventions that we use when we're talking about going around in circles and using triangles to kind of pin down where we're at. Looking at the height on the Ferris wheel as a function of the angle of rotation instead of time. So kind of switching the perspective, where before we were talking about the period being an amount of time to complete a cycle, but now we're going to start basing our height on the Ferris wheel instead of time as how far we've rotated from our starting position. And how do we measure that? Then we'll look at a very important concept called the unit circle, which is kind of like the legend on a map, right? It's how we can scale up those ideas to any circle, any kind of fundamental periodic behavior, things that repeat. Because a unit means one, right? So you can just scale that up to whatever the data says. And then how to think about sine and cosine, some more insights that I just think are important as we're starting off here. So you've probably seen sine, cosine, tangent and hopefully have in the triangle geometry format. And now we're going to start to see how they appear when we get into circular motion. So I want to start with a diagram here with some important information. And I put this here, and I actually want to draw this with you real quick because I think it's important that we put pen to paper. Let me just scoot this down here. I think it's important that we put pen to paper on this because it is it's a different type of graph than we're used to, and so we want to really become comfortable with what's going on. So a few things to note: how we orient ourselves on a circle. So draw yourself a set of axes. And again, if we have some Ferris wheel, you can ignore these details for now. I'll fill you in. The way that we typically describe rotation, so if you get on the Ferris wheel here, the way that we typically describe rotation in the positive direction is counterclockwise. Okay, so that's what I mean when I say counterclockwise is the positive direction of rotation. Now, I remember feeling like that seems backwards, right? Because it's kind of going to the left. But really, it's because of this this concept that comes from Calc 3, which is if you set your right hand on the desk with your thumb out. All right, so I'll draw my terrible picture of a hand. And you see how those fingers are kind of curling. So if this is my desk, my thumb is pointing up off the desk, and my fingers are curling around. That's why we say this is the positive direction. We call it the right-hand rule. And there's actually ways to, say that the other direction is positive, but this is what we say is convention, so that we all know we're talking about the same thing. It's like you could call south north if you wanted to, but why be more confused than the rest of the world? So that's just a little tip on why this is counterclockwise. It's because it's the way your fingers curl when you put your right hand on the desk. And so if you imagine that you're on the Ferris wheel and you are rotating around at some speed, remember that if you're looking at a clock, and I know that this is a skill that's quickly dying as analog clocks are hard to come by, the 3 o'clock position is all the way to the right. The 12 o'clock position is up top. This is a 9 o'clock and 6 o'clock. We call this 3 o'clock position, this is like the starting or initial point. So we'd say the rotation is 0. And the symbol that we use for an angle of rotation, instead of being confusing with just any general input x, we call it theta because it means the angle of rotation. Okay, so if you're up here, or let's say you've gone past, we'll mimic our drawing over here. You've gone past the highest point up here and you're now in this area. If you drew an imaginary line from the center of the Ferris wheel out to where you're at, which is the radius of the circle, right? Then theta is this value here. It's the amount that you've rotated as an angle. So if this is 90 degrees, this is slightly more than 90 degrees, right? Let's say it's like 120 degrees here. Something like that. Okay, so theta is the angle, how far you've rotated from here. So it measures the angle between that initial point, or the 3 o'clock position, and where you're at now. And so we're going to move to measuring your height as a function of the angle of rotation instead of how long it took you to get there. But we'll get there. So if counterclockwise is the positive direction, that means clockwise is the negative direction. So if you have some negative angle of rotation, let's say for example, you have an angle, you rotated, let's say negative 30 degrees. What would that look like? Well, instead of rotating counterclockwise to the left, we go the other direction. So we go clockwise, we'd come out this way 30 degrees, and we'd be somewhere down here. And then you could talk about, okay, well, what's my height at this point beneath my starting position, etc. But this is for negative angles of rotation, and counterclockwise is for positive angles of rotation. So theta is how far we've rotated from that 0 position, from that 3 o'clock position. But again, we're going to move away from the clock terminology because we want to generalize this to just all circles, anything, and all repeated motion. So we have the right-hand rule. Counterclockwise is positive direction. We have clockwise is negative, and this idea theta is the how far we've rotated, and this is sometimes called the radial arm. I'll put this in. Why is it called that? Radial because it's a radius, arm because it's kind of reaching out to that point. So, some things to note here. For this point, let's call it P, my position of where I'm at, I could measure that in space, right? By figuring out how far over I am in the x direction and how far up I am in the y direction, right? In the 2D plane, you only need 2 pieces of information, how far over, how far up. So this P is really the point x comma y and what we're saying now is that these coordinates can be given by the angle of rotation, specifically the height. So let's look at an example down here. So what is my height on a Ferris wheel? Let's say we're pretending we're on a tiny Ferris wheel. Okay, it's only 2 meters across after a rotation of 45 degrees, 270, and 420 degrees. So this is just to kind of get us used to where we're going to be at, as well as how we can measure height. So let's sketch again. Our Ferris wheel has a 2 meter diameter, so that means it's going to be 1 as a radius. So here's our Ferris wheel. And after a rotation of 45 degrees, again, if we start at the 0 point here, the 3 o'clock position, 0 rotation from the x-axis, and we go up 45 degrees, 45 degrees is halfway between 0 and, if this is 90, should be halfway right about here. So here is theta equals 45 degrees. And so the question is, I'm going to make that a little bit smaller here. The question is, how far up in the air are we after a rotation of 45 degrees? Well, before we were able to track it by just dividing out the period, right, into time segments and then figuring out how far up we must be or how far down we must be. But here it's not so clear. So since it's based on the angle, what we can do is figure out, well, this is some point in the 2D plane, so it has to have coordinates x, y. And since we're living on this circle, and we've drawn this kind of the radial arm out to the point P, we can figure out how far over and how far up we are. Right, by figuring out what's this distance that goes right up to and directly under P. This is my x value. And then on the y-axis, how far up I must be here. All right, that has to be the y value, or the height in the air. So how do I find my y value? Well, let's ask, what do we know and what don't we know? Well, we know that this yellow leg here of this triangle we just drew is of length 1. Verify that you understand why. The circle has a radius of 1, right? And I've drawn a point from the center out to the edge. Okay, so I have radius of 1, so that's my hypotenuse of this triangle I've drawn. I have this angle. Hopefully that's helpful. And I'm looking for this side length, right? I want the height in the air, so that's really, I'm looking for y. And what do we have? We have that theta is 45 degrees, right? If we kind of draw out our diagram again with less information, you have something like this. Like, this is what we know that pertains directly to the height y. And so what relates this height y to the other information that I have? Well, I don't know x, so I don't want to include another unknown unless I don't have to. I know this and I know this. Is there something that relates the height of this triangle to the angle and the hypotenuse? Yes, there is. It's the sine, right? Sine of theta is equal to what? Opposite over hypotenuse. That's the formula for sine of theta. And this comes from triangle trig. So sine of theta, in our case, is sine of 45 must equal the opposite, which is y, over the hypotenuse, which is 1. So that tells us that y must be sine of 45 degrees. So y equals sine of 45 here. So sine gives us the height. And this will be the case, since I made this for the arbitrary point P, this will always be the case no matter what theta is, right? So y equals sine theta gives the height as a function of what? Y equals sine of, what's my input? Theta, the angle of rotation. So instead of measuring the time I've been on the Ferris wheel, we can talk about how far I've rotated from the starting point. And so while we're here, it's also the case, and I'd like you to verify that if I wanted to go find x, I know that this would be, using cosine, adjacent over hypotenuse, right? SOHCAHTOA, if you remember that. And so that means that cos of 45, equals adjacent, which is x, over hypotenuse, which is 1. So that tells us that x equals cos of 45 degrees. And so in general, x equals cos theta gives the horizontal distance from the origin. So cosine measures how far over, and sine measures how far up and down. And these functions, if you remember, live between -1 and 1. -1. The range of these functions is between -1 and 1. It's really the percentage of the, if you think of this as like a direction where it's pointing, it's the percentage of how much you're pointing in the direction of either up and down or across. So again, between like -100% and 100%. This is where these numbers come from. I remember no one really telling me that and being kind of confused about why is it between 1 and 1. They're ratios, they're percentages. So what percentage are you pointing up? What percentage are you pointing over? And here, what's interesting is that you get sine of 45 and cos of 45 give you these coordinates. And since this is actually halfway between both, it's the same value. This is radical 2 over 2. You can put this in your calculator and verify that. But you get the same number because it's the same percentage of up as it is over it, splitting the difference. So that's just a nice thing to know. But what do sine and cosine measure? Well, they're related to the sides of the triangle, but then since we can draw triangles inside of the circle to figure out where we're at, they also give us how far over and how far up we are on the circle as we go around, as a function of theta. Okay, so that's just a little bit of exploratory stuff. So to answer question A, the height at 45 degrees of rotation is y equals sine of 45, which is square root of 2 over 2. And I'll just include a little tiny diagram, to signify what we're talking about. So that height is radical 2 over 2. For B, what about a rotation of 270 degrees? Well, let's draw ourselves a new circle real quick. Radius 1. Need to practice my circle drawing on the iPad here. So a rotation of 270 degrees. Remember, we start here, and then we rotate around. 270 degrees is 90, 180, 270, and then full stop right here. And so I'd be at the very bottom of this Ferris wheel, right down here. So what's my height? Well, again, we know that the height is a function of the angle theta, or y equals a function of the angle theta, which is sine of theta. And based on what I just said, let's go around just a little bit of intuition here. If sine is a percentage of how much you're pointing upwards or downwards, right, from 100% to negative 100%, what do you think is happening here? What percentage am I pointing upwards or downwards? Upwards being 100%, downwards being negative 100%. It's downwards, negative 100%. So I should be getting negative 1 as my sine value. And that works out to be true. So what is sine of 270 degrees? It's negative 1. And you see that I'm here on the graph. We know that this angle is 270 degrees. And again, sine tells you the percentage of how much are you aligned with going straight up. And this is the complete opposite of that, right? So it's negative 100%. So I'd like you to put that in your kind of quotes, because it's not, we're not really talking percentages here. We're talking about where it is in space. But I want you to try to build in that intuition about what sine and cosine really mean. So here, the height would be negative 1. If this baseline is 0, and we're 1 below that. Height is negative 1 meters. Doesn't really make sense, right? Maybe this is the ground floor and this is, underground. Doesn't quite matter. It's more about orienting ourselves on the circle. So lastly was, how about a rotation of 420 degrees? So again, let's draw ourselves a Ferris wheel. Luckily I have an undo. So 420 degrees. Well, what do we know about a circle? 90, 180, 270, 360 degrees is a full rotation. So a rotation of 420 degrees means I've gone a full rotation and then some, right? So in your head you could be thinking, well, this is really 360 plus 60, right? This is one full rotation. And here's kind of the extra. So it's like we've gone all the way around and back to our starting position, and then another 60 degrees up here. So here's 60 degrees. Or really you could think of the whole thing, and sometimes you draw it like this, as being 420 degrees. But since it's circular, it's periodic, it repeats, it's the same as 60, right? They're really one and the same. So where do we land? What is our height? Over here. Well, we said height is a function of the angle of rotation. You tell me how far I rotate it, I'll tell you how high in the air you are. Well, the height we know is y. So y is sine of theta. And what's the angle of rotation? Well, we could say 420, and that would be fine. Or we could also say 60. We could say sine of 60 or sine of 420. These are all the same. And we should get radical 3 over 2. Let me just check that. I should have never doubted myself. Of course, it's radical 3 over 2, which is around 0.866. Oh, so you get cocky for 1 second, then you make a typo. So this is the height in the air, around 0.866 meters in the air, or above the ground. So height as a function of the angle of rotation. And again, the same thing for cosine. You can talk about how far over you are, to the right or to the left, based on the input of the angle of rotation. Okay, so some more just important information about sine and cosine. Before we look at another graph. I'm going to do an interactive with Desmos in a second. So sine and cosine, the domain of these functions, what's an allowable input? All real numbers. All real numbers. Anything can go into sine and cosine, which is good because we might want to rotate forward 10 billion degrees, right? Keep going around and around and around. We want to be able to measure the height on the circle. The range, however, keeps us between -1 and 1 for both. And again, why is that? This is the percentage of pointing to the right. And this is the percentage, not percentage, percentage, I'm using made up words here. Percentage of pointing upwards with the radial arm, right? So when we're up here on the circle, we're pointing straight up. And over here, we're pointing straight over. And so when we're in the opposite direction over here, we're at -1 for cosine and 1 in the positive direction for cosine. And up here, we're at +1 for sine. And when we're pointing straight down or hanging below, it's at -1. So it's -100% pointing upwards, right? It's the opposite of that. So this is just kind of some intuition around it. Not totally necessary, but you do need to know these things. Anything can go into these functions, but a very limited number of things come out. It keeps us between -100 and 100%. So with that, I would like to show you some things that happen. So this was all based on what we call the unit circle. And we've drawn it many times, but we haven't necessarily called it that. And this just means a circle of radius 1. And why that's nice is because, again, you can use it and then scale it up to whatever the circular motion you're dealing with is. If it's a Ferris wheel, great. If it's something else that repeats, like a population's cyclical levels, or the tides, or anything that it repeats, then we can scale it, since this is a unit, just like you can scale the number 1. So let's draw this one last one. We'll label it really good. So here's 1, -1. And again, here's a point x, y, which we know has the coordinates cos theta, sine theta at any point. Where's theta? We didn't label that yet. Theta is the angle of rotation here, or the angle of rotation here. So how far did we spin around? And then we can tell you, since we're really doing what? Inscribing these triangles, that's how cosine and sine get involved. So it's kind of like, circles and triangles are like the building blocks of just all shapes. It's like the simplest closed shapes you can have. So it makes sense that they would play together in this way, that triangles and circles would both involve cosine and sine. So that's the unit circle. Radius 1, you can tell where you're at using these. Now, if you want to scale this up, right? Let's say I don't have a circle of radius 1, but I have a circle of radius 50. Right? What happens? Well, it turns out that just everything gets scaled up by 50, right? Because now this is no longer a hypotenuse of 1. This is hypotenuse of 50. And so then these sides get scaled up by 50 as well. So that affects these two. This becomes now 50 cos theta, 50 sine theta. And since I made up that number, that radius of 50, this works for any radius that I might want to make up. All right, so let me backtrack here. And do it in general. If I'm out some radius here, r, and it's not just a unit circle, it's circle of radius r. Could be 50, could be 10 billion, doesn't matter. That makes this radius r, which makes this point xy equal to r times cos of theta, r times sine of theta, right, where this is my angle of rotation. So r scales up the unit circle, whatever that radius might be. Okay, so let's take a look at a animated graphic, because it can do a better job than I can drawing circles, and we'll chat about it a bit. Okay, so let's get this thing going here. So I've got the equation for a circle here. You might remember its general form, x squared plus y squared equals r squared. Well, with the unit circle, r is 1, right? So here I am on the on the unit circle. I won't change that. And I've labeled my coordinates of the point on the circle with this radial arm as I'm going to spin around. A is my angle instead of theta. My angle of rotation. As I increase this, you'll see what happens to my x and y coordinates. So if I come to 45 degrees like we were before, you see, okay, look, I'm pointing in the same amount up as I am to the right, and so those percentages are going to be the same. 45 degrees is a special angle because of that. It's the ideal angle to launch a projectile, right? Because it's going to go the furthest because you've maximized the upward and outward directions. But anyway, as you increase the angle A, you see what percentage am I going in the upward direction versus the over direction. I'm only like 22% pointing to the right, and I'm 97% pointing straight up. And as I move up to 90 degrees, I should be all the way pointing upward and not pointing at all to the sides, right? So again, my height is a function of the angle. 90 degrees, I should be at 1. And as I increase my angle and go around, you'll see this continues, even in the negative quadrants, right? So 180 plus 45 degrees in this direction, completely opposite of this one. I'm at negative 0.07, negative 0.07. I'm down in quadrant 3, where x and y's are both negative. But these ratios are still the same, the percentage of this direction versus this direction, but they're just negative because it's left and down. And this will continue as I go all the way around and then pick up and repeat again. So after 360 degrees, it's like you reset and the same pattern happens. So again, this is what I mean by seeing the triangles inside the circles as these kind of fundamental building blocks of just shapes of where we're at. And they're obviously going to play a key role here in periodic motion. So this is the unit circle. And again, you would see that if I had a circle of radius 2, if these are the percentages of how far I'm pointing this way versus this way, these points would stay the same if I increased it to 2 and nothing happened. So these also have to get scaled up by 2. So you'll notice here I have r times cosine A, r times sine A, because if my radius changes from 1 to something a little bit bigger, that means this radius is increasing, which means how far out I go and how far up I go also have to increase by that same scaled amount, right? So they got to keep up. So if I increase the radius to 2, you'll see, okay, this is twice what those percentages were. The percentage thing kind of breaks down now because it's no longer the unit circle, but your x and y coordinates are still dictated by the angle of rotation. So 45 degrees. Oh, this should be 45. 45 degrees. And then the cosine and sine of those times the radius so that you've gone out far enough. And obviously you can shrink the radius as well. Let's say from 0 to 10. Can shrink the radius as well. Make it get bigger, it could get huge, right? And these are still going to be giving you the coordinates on the circle, as long as you scale it up, okay? And if you don't, if r is 1, then you're on the unit circle. But this is the beauty, what I'm trying to say of the unit circle is that you can use r to get it to whatever the data you're looking at reflects. And if it is as simple as a Ferris wheel, and it's 250 feet across, then your radius is 125, and then the unit circle, boom, becomes the circle that you care about. So it's kind of like our template, our copy-paste tool for everything. So that's a lot about the unit circle, sine and cosine, what they really mean. Let's go back to our notes here. You learned about how we orient ourselves using the right-hand rule. Counterclockwise is the positive direction. You know how to talk about height on the circle as a function of angle, not as time. You learned about the unit circle and why it's special, and how to think about sine and cosine, both as this SOHCAHTOA kind of thing that we remember from triangle trig, but also as the percentage that you're pointing upward or to the right. And they can eat any number, right? Their domain is all real numbers, but they only spit out numbers between -1 and 1. So I hope you enjoy practicing some problems here in 7.2. And in the next unit, we're going to be looking at a different way, and it's a better way, I think, to measure angles than using degrees. In a similar kind of way that, metric sometimes beats using the English standard system, using radians beats using degrees, especially for those of us on our way to calculus. It's just way, way better. But anyways, my bias aside, I will let you enjoy practicing these problems, and I'll see you in the class discussion.